Hi everyone, I'm Jung Park from Seoul University. Today I'll talk about MDC, which is a memory dump-based checkpointing scheme to address the memory footprint issue in the existing fork-based checkpointing. Let me briefly explain what fork-based checkpointing is. Long-running applications, especially in memory databases, require constant checkpointing scheme for fault tolerance. For example, Redis and Hyper use a fork system call to take an in-memory constant snapshot of a point-in-time data. As all you know, fork system call creates a child process sharing a copy and write mapping with its parent process. So after fork, the parent process can handle client requests while child process traverses and writes data in a file in background. Due to their behavior, we call the child process checkpointer and the parent process servicer. Servicer and checkpointer shares a copy and write mapping. So when a DB client sends update request to servicer and servicer tries to update the contents of the shared pages, then copy and write fault occurs. In such a case, the corner fault handler allocates a new page, copies the faulting page to the new one, changes the PT mapping, clears write protection bit in the PT, and finally performs TLB flush. This prevents checkpointer's point-in-time snapshot from being inconsistent. However, let's think of a situation where all the shared pages are touched and copywritten during checkpointing. In such a case, the memory usage can be increased by 2 times. However, the problem is that this increased memory cannot be reclaimed until the checkpointer finishes the job and terminates. One may think that freeing the checkpointed object in checkpointer is enough for reclaiming memory. But actually it is not, because of the semantic gap between in-memory database and operating system in the context of memory allocation and deallocation. This gap comes from the presence of the user-level memory allocator such as GNU libc allocator and JEmalloc. They help applications to efficiently allocate and deallocate memory at object granularity while minimizing the OS's involvement. For instance, the memory of the freed object is not immediately returned to the OS but is recycled for the application's other memory allocation requests to avoid excessive system call overhead. So the memory allocator keeps the memory once allocated from the OS until the process terminates. So the time it takes before the checkpointer's memory is released depends on the checkpointing speed as well as the update intensity of the workloads. The slower the storage device, the longer the checkpointing time, thus the higher the chance of memory being doubled for update-intensive workloads. Now we know that memory consumption can be doubled during checkpointing for update-intensive workloads. So let's see why this can be a problem. First, it can cause memory pressure, which consequently harms the performance of the in-memory database owing to swap, or even results in the in-memory database being killed by the OS's out-of-memory killer. So, in-memory database vendors recommend users leave enough memory for the OS to prevent memory pressure. However, this conservative approach leads to wastage of memory, which can be used for storing more data. So then, how can we mitigate this problem? We cannot prevent the copyright faults from happening once the write protection bit in the PT is set after fork. However, in Linux kernel, there is an interesting optimization for a special case where the faulting page is private. Here, private means that the page is mapped to a single process's address space. In such a case, the copy and write fault handler allows the process to in place update the faulting page, so the memory usage is not increased. This also helps to reduce the latency of copy and write page faults, skipping page allocation and page copy. To make shared pages private, either parent or child process must voluntarily return the memory of the pages to the OS, so that the OS unmaps the pages from their other space. The unadvised system call with the don't need hint can do the job. So our idea is simple. Let's return the checkpointed pages to the OS as soon as possible. However, there is a problem. It is working granularity difference between M-device system call and databases checkpointing. In-memory database performs checkpointing at object level, while M-device works only at page level. Because multiple objects can be stored in a single page, the page cannot be returned to the OS until all the objects within the page are checkpointed. One may think of a naive solution using bitmaps to track the checkpointed objects within a page. However, this requires management costs in terms of memory usage and CPU cycles. Moreover, even with this solution, pages still cannot be readily returned. This is because checkpointing order is not the logical address order, so two consecutive objects within a page can be checkpointed at two very different time points. And because some of the objects, for example temporary data, may be not meant to be checkpointed, thus only one tiny object left uncheckpointed can result in the failure of returning the pages to the OS. To end this, we present a new fork-based checkpointing scheme called MDC, Memory Dump-Based Checkpointing. MDC exploits physical memory dump to create a physical snapshot of database rather than a logical snapshot. Physical memory dump allows the pages to be released in a sequential logical address order as soon as they are written to disk. For restoring the original data from the physical memory dump, MDC logs the virtual address of the object instead of writing the objects themselves. I'll explain how it works in later slides. MDC's checkpointing model is very similar to the existing fork-based checkpointing schemes model. You can see how they are alike in the figures below. In the existing one, after fork, checkpointer traverses objects, and for each object, writes the type and size of the object and the object itself. In contrast, MDC's checkpointing model has 3 steps: preparing step, logging step, and lastly memory dump step. They correspond to MDC checkpoint start, MDC app write, and MDC checkpoint end function calls, respectively. MDC app write requires one more argument representing the checkpointing type. With the MDC value type, MDC app write works the same way as app write. While with MDC reference type, MDC app write the address of objects instead. We chose this non-transparent approach because application knows better than the OS where the object is allocated. However, even with the non-transparent approach, applying MDC to existing application requires only few changes. For example, only 50 lines of code are required for Redis to use MDC. Now I'll explain how it works in detail. In this presentation, I'll cover only the checkpointing procedure. Please refer to the paper for details of the restoring procedure. Let me start with the preparing step. When an application calls the MDC checkpoint start function call, MDC prepares several things for internal use before checkpointing. First, it allocates address space table in memory, then load the VMA information into the table. Each row of the address space table is associated with a VMA containing the start and end address of the VMA and a dump flag, which indicates whether this VMA needs to be memory dumped at the end of checkpointing. And finally, it creates 3 files for internal use. Dump file is used for physical memory dump. VMA file contains the information about the dumped VMAs, while bitmap file stores the bitmaps that indicate which pages in the VMA are written to the dump file. After all these are done, the preparing step is completed. For the logging step, let me show an example. Let's assume that we have a memory buffer that contains a string object hello world whose type is 0 and size is 12. Let's say the address of the object is 1447010 in hexadecimal. When a database wants to checkpoint the object, it usually writes the type and size of the object as well as the object. Here we use MVC value type for type and size because they are small and located in stack. So we use fwrite for these. But for string object, we use MDC reference type because it is larger than 8 bytes and located in heap. For this case, we first find the VMA of the object virtual address and sets the dumped flag to 1 if not set. Then we write the address of the object. This is the logging step. The last step is the memory dump step. It starts with an application calling the MDC checkpoint and the function call. We first check which VMAs have their dumped flag set to 1. For each target VMA, we store a VMA entry, a bitmap entry into the respective tables. They are used later for restoring to find the file of set of objects within the dump file. We perform memory dump at multiple page granularity. The default setting is 64 pages, which is empirically decided. As soon as we finish the memory dump of 64 pages, we return these pages to the OS using M-advise system call. Then we finally close the opened files. For restoring, we can read the address of the object from the checkpoint file first and find the file offset at which the target object is located while working the VMA table and bitmap table. For evaluation, we use 2 machines, one for client and one for server. Each has 32 GB of memory, and the server machine has 2 SATA SSDs for swap and checkpoint respectively. We apply MDC into Redis and run it on the modified Linux to support MDC. We use YCSV workloads to evaluate the performance of our scheme. We run the YCSV workloads while enforcing the Redis to start checkpointing in background, so that we can know the performance during checkpointing. This figure shows the memory footprint with varying dataset sizes when the update proportion is fixed to 0.5. Yellow bar represents the dataset size, red and green bar are the increased memory during checkpointing for Redis fork and Redis MDC respectively. Red and green lines shows the increased memory footprint relative to dataset size. As you can see, register-focused memory footprint can be increased by up to 77% relative to the dataset size, but only 26% for Redis MDC. Note that our machine has 32 GB of memory, so that beyond that limit, swap can occur. You can see that for 60 million records, Redis-focused memory footprint exceeds the system memory limit, even though the dataset size is only 21 GB. This figure shows the throughput of the YCSB workloads with the same configuration as the previous one. We find that when system memory is enough, Redis MDC offers only a marginal performance improvement by 1.5 on average over Redis fork, avoiding some page duplication on copyright faults. However, when the dataset size is larger, the throughput of Redis fork starts to drop severely due to swap. In contrary, under the same condition, Redis MDC maintains the throughput thanks to the decreased maximum memory footprint. To analyze how the memory footprint changes, we plot the memory footprints of Redis fork and Redis MDC over time for the 13 million records. The Redis fork's memory footprint is incrementally increased over time until checkpointing finishes. On the other hand, Redis MDC finishes the logging step within 11 seconds after checkpointing process starts. It then starts to perform the physical memory dump while returning the pages to the OS. As a result, the increase in memory footprint starts to slow down after that. The memory footprint starts to drop at 24 seconds because as the number of pages returned to the OS increases, the chance that updates do not result in page duplication will increase. In summary, our scheme can halve the amount of memory increased during checkpointing. To conclude, fork-based checkpointing is powerful due to the simplicity yet state-of-the-art performance. However, the increase in memory footprint issue is an unsolved problem of the fork-based checkpointing. To end this, we have presented MDC exploiting physical memory dump with the help of DOS. Our results show that our scheme can effectively mitigate the memory footprint issue so that memory that has to be reserved for the worst case can be used for storing more data. This is it. Thank you for listening. If you have any questions, please feel free to ask by email.